Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 13 Periodic Motion Video 4. Today's topic is energy in simple harmonic motion. The objectives are: know that total mechanical energy in simple harmonic motion is conserved. Understand the graphs of E, K, and U versus X. Be able to use energy concept to analyze simple harmonic motion. TME in simple harmonic motion is conserved. Since the force exerted by an ideal spring is conservative, and the vertical forces, that's the normal force and the gravity, they do not do work. So the total mechanical energy of the system of a body in simple harmonic motion is conserved. Assume that mass of the spring itself is negligible. So the total energy at any time is its kinetic energy plus its potential energy. That should be constant. We also know when x equals to a at its maximum displacement, velocity equals to 0. So at this point, we know the energy is entirely potential. So the energy at that point is 1/2 Ka squared. Since E is constant, it equals to 1/2 Ka squared. That is the total energy. So we can rewrite this equation as at any position, it's kinetic energy plus its potential energy equals 1/2 Ka squared. We can determine Vx, that means we can determine velocity when given the position from that equation. So Vx equals to square root, positive or negative square root of K over M times square root of A squared minus X squared. So basically we divide by 1/2 on both sides, and we subtract kx squared on both sides, and then we divide m on both sides. The plus and negative sign here means that at a given value of x, the body can move either to the left or to the right, or up or down. For example, when x is positive or negative a, we can find Vx. Vx equals to positive and negative k over m times a squared minus a over 2 squared. That actually gives us square root of 3 over 4 can be positive or negative times k over m times a. So when x equals to 0, we know v equals v max. So what is v max equals to x equals to 0? That is just k over m a. K over m, square root of k over m is omega, so that equals omega a. This max means the positive value. The minimum is the negative value. Let's take a look at the diagrams. The diagram is E is always constant. So in all this case, E is the brown line. The height of the brown is always the same. So at one point, all the energy can be in potential. In this case, when a slider is at negative a, all the energy is in potential. So potential plus kinetic equals to total. So U is all the energy is potential energy. When it is at negative 1/2 of a, so some of it is potential, some of it is kinetic. The two added together equals to E total. Actually, in this case, K has more, right? 3/4 of the total energy, and the potential energy is only 1/4 of the total energy. At x equals to 0 equilibrium position, all the energy is kinetic. All the energy is kinetic energy. And again, at 1/2 a, the positive. So in this case, still K is 3/4 of the total energy. You have the same energy situation as when x equals negative 1/2. Here, similarly, at a positive A position, the energy situation is the same as negative A at x equals negative a position. Now let's take a look at kx and graph and ux graph. So these are the graphs. K is the green line. So in the middle, K is maximum. Blue line is U in the middle. U is the minimum. The two added together equals to E. As a matter of fact, E is constant at all point of x. So U and K plus add together equals to U. At this point, the energy is half of kinetic and half of potential. This position, however, is not X. X is not 1/2 of A. It looks like it's more toward the end than in the middle. Let's see, what is the value of X when K equals to U and K plus U equals 1/2 Ka squared? So what is this position X? We can figure it out. Since K equals to U, so we set K equals to U, that becomes U plus U equals 1/2 Ka squared. U, so 2U equals 1/2 Ka squared. U equals 1/2 Kx squared, that means 2 times 1/2 Kx squared equals 1/2 Ka squared. So X is just a plus and minus square root of 1/2 times A. So that's the position. What is the value of Vx? What's its velocity when K equals to U and K plus U equals to 1/2 Ka squared? So now, since we're trying to find velocity, we have to substitute U as K. So we have 2K, that equals to 2 times 1/2 mvx squared equals 1/2 Ka squared. So we can find Vx equals square root of 1/2 of a maximum velocity. This Vx, it should be positive and negative also because it could go either way. So I forgot a positive and negative sign. I have it over here. I forgot it here. Okay, let's take a look at this example. So in the oscillation described in the previous example, when K equals to 200 newtons per meter, and the glider is 1/2 kilograms, an oscillating mass released from rest at x equals to 0.2 meters. That means phi equals to 0 in this case, right? Find the maximum and minimum velocity attained by the oscillation. So maximum velocity is positive omega times A. Minimum velocity is negative omega times A. What is the maximum acceleration? Maximum acceleration is positive value, omega squared times A. So it's equals to 8 meters per second squared. Then minimum acceleration is just negative 8 meters per second squared. What is the velocity and acceleration when the body moves halfway when x equals to 1/2 of A? What is the velocity? We can use Vx equals to this as a function of x. We substitute x equals to 1/2 of A, so we have negative 3.5 meters per second from its original path. The velocity, so I guess this means when A is positive, okay? What is the total energy, potential energy and kinetic energy at this position? Here is A. A equals to the negative. When x is positive, A equals to negative. Find the total energy, potential energy and the kinetic energy. Oh, so the acceleration is negative because x is positive. So determine the velocity acceleration when x is halfway to the center from its original position. So originally it's positive 0.2. When it goes back, x is still positive. That's why I guess Vx has to be negative and A is also negative. Find the total energy, potential energy and the kinetic energy. Well, total energy is 1/2 Ka squared. Potential energy is 1/2 Kx squared. X in this case is A over 2. Then K is 1/2 mv squared. So we did this before. In the half position, you'll have more kinetic energy. Kinetic energy is 3/4 of the total, and the potential energy is 1/4 of the total. Okay, another example. So this one, a block with mass m attached to a horizontal spring with a force constant K is moving with simple harmonic motion having amplitude A1. At the instant when the block passes through its equilibrium position, a lump of putty with mass m is dropped vertically onto the block from a very small height and sticks to it, that means its horizontal velocity equals to 0. Find a new amplitude and the period. So first, let's see, before the collision, the total energy is 1/2 kA1 squared, and that equals to 1/2 mv1. v1 is the velocity at equilibrium position. So we can find the velocity of the glider equals to square root of k over m times a1. And it's moving to the right, therefore it is positive. Since the momentum is conserved and the body's velocity equals to 0 before, so we have v2, the total velocity for body and the glider's velocity after the collision is the mass of the glider divided by mass of the body plus mass of the glider times the initial velocity of the glider, v1. So E2 was the total energy of E2, that should be equals 1/2 kA2 squared. That should be equals 1/2 mv2 squared. So we substitute v2 equals to this. So we have A2, then you'll have v1. So this is just algebra. A2 ended up to be equals to A1 times square root of m divided by m plus m. As you can see, A2 is less than A1. That makes sense, right? Because you're slowing down after collision, so your amplitude has to decrease. What is the period? Period equals to 2 pi. Since your mass increased, so your period has to increase. So it's going to be vibrate a little back and forth slower. Part B, repeat for part A for the case in which the body is dropped on the block when it is at one end of the path. When the body drops, the block at this end is at rest, so both momentum and kinetic energy are 0 before and after the collision. Therefore, the energy is all potential energy stored on the spring, so total energy doesn't change, still is the same. Adding the extra mass of the body has no effect on total mechanical energy, as a matter of fact. But we know the velocity in the middle should be smaller because the mass has increased. Next one, total energy is the same. Velocity is smaller because the total mass has increased. However, the period still is the same. So the period has nothing to do with amplitude. Remember, period only has to do with mass and k. Since mass did not change, k didn't change, so period didn't change. Period is still the same. Okay, test your understanding. To double the total energy of a mass spring system oscillating in simple harmonic motion, by what factor must the amplitude increase? So total energy equals 1/2 kA squared. So A is proportional to square root of E. So if E doubled, A has to increase by square root of 2. So the answer is C. By what factor will the frequency change due to this amplitude increase? Remember, frequency is not affected by amplitude at all, so frequency stays the same. It does not change. That's it for today. Thanks for watching. See you next time.